Everyone, today we'll be talking about Bloom filters. So let's get started. So everyone knows about hash map, right? So in hash map, what do we have? We have a hash function. So hash function gives us hash code, and then we go to the hash code address, or we go to the bucket corresponding to the hash code, and then we put in the value, right? So this is how hash function works. Put or get the value. Correct? Now, Bloom filter is basically a lightweight hash map, lightweight version of a hash map. So what do I mean by lightweight version of a hash map? So in Bloom filters, we have some kind of, let's say, um, but before that, let's first understand what Bloom filter actually does. So let's say I want a data structure in which what happens is that, let's say I have a data structure. I have a lot of elements in here. Fine. So now I want to keep a track of the elements seen thus far. So I want to keep a track of seen elements. I don't want to necessarily store the elements. I just want to make sure that I have a track of the seen elements. So in that case, we have Bloom filter. It will say that either we have seen this element or not. It has its own trade-off, and we will discuss it. What is the trade-off? So, let's get started with how it happens. So basically, first let's understand what is the use case. So in Bloom filters, there is one thing which is like, there's a possibility of false positive. What is false positive? So by false positive, I mean that, you know, if let's say I insert an element. So my Bloom filter will say, if I search for that element, it will return true. I have not inserted some element, or that element is not seen. Very less chance that Bloom filter says, I have seen it. So this is the trade-off, which is not the case in hash function, right? In hash function, when you do a get and put, that is taken care of. So the possibility of this is there. Possibility of false positives are there, but it will never say that if you insert an element and if you ask if you have you seen this element, it will never say no. So there's no false negative, but there are chances of false positive. So this is the trade-off for Bloom filter. Now, what do I mean by this? When you but also there's an advantage. What's the advantage? The advantage is that, or the advantage is that, yeah. So the advantage that I have is it is space optimized. So let's say if I have an IP address of 32-bit. Now, if I have an address of 32-bit, my Bloom filter will not store 32-bit. It will just store, I will do some homework. So it will just store that many bits. So it will, let's say, I decide on the number of bits per object. This is something I have to decide. So it will only store those many bits per object. That's it. And we also have to decide K. We'll get to a point where we decide K. So in Bloom filter, we have K, which is number of hash functions. So in this, we don't have a single hash function. We have K number of hash function. So what do I mean? Let's say if I first let's understand the use case. So the use case is that, let's say I have a dictionary of words. What do I have? A dictionary of words. Fine. So I want to maybe create a spell checker. Fine. So if I want to create a spell checker, so in this, I can't, if like, let's say I'm having a Word document, fine. So let's say I have this Word document. In this Word document, I'm typing some letters one by one. Okay, typing some words one by one. So after I type this word, what will happen? Will my spell checker go and check for this word in the dictionary and see if it is not there? Then go and check for this word in the dictionary? No, it will not do like this. Rather, what it will do is that it will keep a bloom filter. What do I mean by bloom filter? It will have a bloom filter. So, what will bloom filter do? Now, my bloom filter will, uh, it basically has k number of hash functions. For example, I've done my homework and I've come up with this thing like I have decided my k is 2, let's say. So in this case, what I mean to say is that let's say I have a string. Okay, this is my word. Now I will have two hash functions. Fine, since my k is 2. Now let's say these two hash functions gave me some value, let's say 26 and let's say 14. So I will go to the bucket 26, set the bit to 1. And also remember the objects, the value that we are going to store is only 0 and 1. So that way we have optimized the space. And also to the bucket 14, we will go and set it to 1. It will be 0 initially. The buckets will have been initialized to 0 and then we'll set it to 1. Now we will understand what happens when we search for that string again. So it will, we'll just walk through the footprint. So what is the footprint? The first hash code was 26, the second hash code is 14. It will go and check for if that bit is set to 1. And if this bit is set to 1, if all the bits are set to 1, we have seen that number and it will return true. Correct? So this is how it is optimized. Now let's see why false positives happen. There's a case false positives happen. A number was not there, but it can say it was present. So let's see why. I'll tell you. Let's say I have a word, okay? And let's say the bloom filter gave it maybe 18 and 25. The hash functions gave it this hash code 18 and 25. Fine. And now let's say I have another string in which the output was, let's say, combination was 26 and 25 and 26. And this was 26. Now you see 25 and 26 have been set to 26 is overlapping from here and 25 is overlapping from here. So 25 and 26 have already been set to 1. So in this case, it can say 1, although it was not seen. You understand the reason why? So yeah, so this is the reason why there can be a false positive. Okay, now since we've understood this, then now let's see if how can we avoid this. So there's a trade-off that we can do. So first let's understand the use cases. So first use case is spell checker, of course. Second use case is, let's say I want to keep a track of all the, you know, like blocked or harmful website links or IP addresses. So then third use case can be over the, router specific software. So all of those things can be handled using Bloom filter. Now, let's go ahead and see how do there's a thing that, to minimize the error, the ideal way to set K is 0.67 times number of set bits. Number of set bits to actually minimize the error. To minimize the error. This is what we should do. So how? Number of set bits. So let's first say number of set bits. We have to think of number of set bits. Let's say we have decided on number of set bits, maybe 18, 16, 24, anything. So my case should ideally be something similar. It cannot be exactly since it will be decimal number. So 0.67 into, let's say I've decided 8. So 8. So my K should be this value. Now, if I calculate 0.67 into 8, 0.67 into 8, it comes down to be 5.36. So my K should be roughly equal to 5.36. So we can either take 5 or 6 as, just the non-fractional part of it. So this is how we can minimize the error. So if we take this, the chances of error is basically maybe close to just 2%. So yeah, this was it from my end. This was all about Bloom filters. And we have to do some trade-off. It is a lightweight version of a hash map. It can have false positives, but it will never say that I have not seen an element when it has actually seen it. So it is optimized in this way because it has k number of hash functions. And let's say if I have an IP address of 32-bit, so what happens if I have an IP address of 32-bit? It will not store 32-bit. It will just store the number of bits per object into K. So this is the advantage we have. So yeah, that was it from my end. Thanks for watching. Bye.